Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. And that's this video here right now. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
All right, so this is the program Andrew had you write. This is our super top secret, highly sought after, very expensive piece of software that says, please enter a product key, and then either we get the key that was correct, we get the full access to the product. If not, we just get invalid key. And the thing that made this really challenging is Andrew set the product key to a random number. Right, so it's very unlikely that we're ever going to guess this number. No one got it on their first try last time, right? Does anyone remember the odds of getting that number? It's like 1 in 4.29 billion, right? So you probably have better odds out at slot machines just across the hallway here. So what our goal was to do in this program is to change that compare statement where it says if the key is equal to random, and the result of that comparison, we just wanted it to jump down and say, no matter what, we have the full version of the product. So a couple different ways we did that. The first one was actually running it through in our debugger. Does anyone remember when we used GDB, what we switched to make that compare statement true? Yep, so the first way we went through is that we actually set the registers that were being compared. I think it was EAX and EDX, and we just set those to be the same value so it would jump through. Andrew then had you guys make a more persistent patch in Radar 2, and that was basically just switching that jump, so we're changing the logic. If the key didn't equal the random number, then we'd say we got the full version of the product. So that was a very effective way of getting around that too, because those odds of us actually guessing that real number are so small, it just wouldn't really matter. But we're going to make it one better today. We're going to make sure that we always get the product key correct no matter what. So we'll make a persistent patch. We can always go through it and always get the correct answer. So keep in mind the larger context of this is when we look at something that's like maybe a piece of malware, they're going to put in some anti-debugging techniques so that we can't watch that as the analyst. And if we can identify some of those anti-debugging techniques, we can change the logic of them, much like what we're going to do today here. So there's kind of a bigger picture of what we're looking for in that. So let's go ahead and open up a terminal here and just recompile this program, because your programs are probably patched from yesterday. So we'll just recompile it, create a fresh copy of that program, and then we can open this up in Ghidra and look at how we can patch it there. So I'm going to jump over to my desktop. Is that where you all saved your programs? Okay, or whatever folder you saved it into, you just navigate there. And we're compiling this with GCC, and I gave it the -M32 to make it a 32-bit binary. And the only other thing that we really did was just set the output name, right? So I'm going to call this Who's got a creative name for today? Vegas.out. Okay. So our program's source code is example.c. And then we can do a -o, lowercase o, and we'll do Vegas.out. When you have that recompiled, just go ahead and run the new binary. Make sure it works. And then we can tackle that one here. So instead of doing this in Radar 2, we're going to open it up in Ghidra. I like working in Ghidra because, like we've seen, we have the graph views, has a pretty nice interface. It's easy to make these patches and changes. And so we can also launch some scripts that are going to put these binaries back together appropriately so that they still run when we're done with our patches. So the shortcut on top of this VM is broken, so just run it from the command line. And you can just type Ghidra. And that will launch our program here. And the first thing that we're going to have to do is import that new binary file into our project. So the way I like to do is just hitting I on your keyboard. You can go to the file menu and grab the import from there too. But I'm going to import Vegas.out. And like what we looked at yesterday, when it opens up an executable file, it can read that file header and get some basic information about how that program was compiled, what architecture it was for, and those types of things there. So we can see it's the Linux executable format. It's 32-bit binary, so kind of all the things that we'd have expected from that. Now, why is identifying the compiler important for us? Like, why would I care what this program was compiled with? Yeah, because the different compilers, like what we looked at the beginning of yesterday, are going to give you different output. So if you know how something was compiled in the first place, and you're kind of trying to match up that source code to it, you can write those same structures in C, and then see if your logic or understanding of it was correct. So go ahead and import that. And then if you just double click on Vegas.out, it's going to open up the code browser for us. And when it asks you to analyze it, just accept the defaults. So you can hit OK here on the next screen just to analyze. Okay, so that one imported pretty quickly, right? Small program, pretty simple, nothing weird going on with it. If you go underneath the symbol tree on the left-hand side here and expand out your functions menu, if you scroll down a little bit, you should see that main function. And if you click on it, it'll bring you to our program here. We can see it in the code browser and then the decompiled view as well.
Referring back to a question from yesterday, this is a really good example. The question was asked, could you take the decompiled source code and recompile it? And I think this is a great example of like, it's really close, but things like undefined for are not going to compile. Undefined for means it's returning a 4-byte value, a 32-bit value, but we don't know what that is. So the source code is close enough that you can understand it, but it would take a little bit of human manipulation to get it to the point where you could actually feed it back into a compiler. So I don't mean to detract from your lesson.
No, that's a good point there too.
Really good example of that.
Also, you see stuff like this, like the local 10 equals the address of something on the stack. Like that's not going to be in our source code, so that'll cause some problems for us too. Can we actually change the?
Yeah, do retype. Do int.
So why did it say undefined for?
It just knew that we were returning a 4-byte value, but it didn't know like specifically what that was. Typically, just looking at the context of it, we know it's usually int main. So we want to return that number back if it was successful in its execution or things like that.
So it's another data type that has 4 bytes.
Float pointer on 32-bit.
So when you change that to decompiler, it doesn't change anything here with assembler. You check the decompiler view.
Yeah, just changed it in the decompiler view.
So does that mean when you have a shared project, other people can see that as well?
This should be able to, right?
On a shared project?
Yep.
Yes, but only once you have committed your changes to the shared server. So think of it like a Git repository where the changes that you make locally will only become visible to others after you push to the server. So yes.
So it's kind of asynchronous changes. Yeah, another thing that I would just recommend, and we haven't spent much time on this, but as you're going through a program, when you figure out what things actually are, it's a good idea to rename them. Just like when we add comments to our code, give yourself some context of what you're working with there. So when I look at this call to scanf, I know that the number that the user enters is going to get stored in that second parameter there. So what I might do is click on that local 14, and if you just type L, that's an easy way to relabel something. And I might just change that to be something like user input. Right, so they seem like pretty trivial steps, but the more clues you can give yourself, I think it's really helpful to come back and visualize what's actually happening in there. We also know ivar1 is equal to that random function, so that's going to be that generated product key. So I might do the same thing there and just hit L and just say product key. Right, so it paints that picture a little bit better of what you're looking at there. So our job was to make this logic so that we always end up in the printf statement here that says welcome to the full version of the product. And actually, since I said printf and it clearly says puts, does anyone know what's going on with that? It's optimized for what conditions?
For a string that just has a new line.
Yep, it's for a string that doesn't take any parameters, so there's no %d or %s, and it has a new line character at the end. The puts function's actually more efficient or more optimized than printf. Does the same thing at the end of the day, it's just one of those compiler optimizations that we see. So if you click on this if statement, in the code browser on the left-hand side, it'll actually bring you to where that comparison's being made. So that's one way I like to use that decompiler along with the code browser. I mean, it's just easier to look at that decompiler view than this huge listing. Another way you can do that too is if you click on the graph button up here at the top. So it's kind of right next to that green play button. You see a similar image to what we saw in IDA Pro. And I think this is where Andrew and I were talking about. It doesn't look quite as nice as what IDA's graph view has, but the same information's there. So when we get to this jump not 0, right, if it's false, we're going to follow that red line. If it's true, we follow the green line and end up in that. So do we want this jump not 0 to be true or false based on this graph view? We want it to be false, right? The clue there is we can see that product key string getting pushed onto the stack here. So we want to make sure that that jump is false, and we end up in that code block. I'm going to go back to the code browser here and see what ideas you all have on how we can make this thing always go to this line here. Welcome to the full version of the product. Or to that code block anyways. We can change the compare to what? So if we change the compare to product key and product key, let's see what happens over here in the decompiler view. So you can right click on that line there where we have the compare and go to patch instruction or Control-Shift-G. And I love this because it's a little more straightforward to change those instructions. So when we did it Andrew's way, we looked up the bytecodes in that assembly website, just patched it straight into hex. If you don't know those bytecodes or not quite sure what you're looking for, this is pretty nice because we can just type what we think it should be. And it gives you some valid completions for that too. So if I want to change this from compare EAX EDX to EAX EAX, it gives you the bytecodes there as well.
Can you show me how do you do that? You right click? Or?
Yep, so I right clicked on it and then went to patch instruction. So looking at the decompiler view, there's a couple cool things happening here. Your guys' patch was right. So we compare EX, EX, it's always going to be the same value. So that jump's always going to be taken here, or not taken. So you can see in the decompiler view, it just says we're going to generate a random number, print out welcome to the full version of the product, and then exits the program. And what Andrew just mentioned is that's a way that Ghidra is optimizing out what it thinks is dead code. So it saw that that code block saying invalid product key is never going to be executed based on how this program works. So it just hid that from you. So it doesn't really give you the whole picture of what might be there.
That's also a really wonderful illustration of another question yesterday about, like, why is it still important that students learn assembly code and be able to do this in assembly rather than just using the decompiled view? Like, obviously in this program that is dead code, it will never be reached. But you could imagine conditions where the program somehow jumps back into that code block indirectly via a pointer calculation or something. And in that case, what is now hidden from the reverse engineer is something valid that we should use.
I have a real life example for you.
So will Ghidra tell you which parts it thinks is the dead code, or you gotta?
Not that I'm aware of.
Okay, gotcha. I think it just won't highlight. So like when you click through the lines of C code, it will highlight what assembly code corresponds to it. But you just have to notice that there's some code being skipped.
Okay.
At the top, there's a warning that says remove your unreachable block.
Oh. There we go.
You can go to the settings and tell it to actually show those.
Where do you go there for
How
that?
do you do that?
I think it's under analysis, edit tool options. And then if you go to the compiler analysis,
Oh, I didn't get that.
you can uncheck the eliminate.
Nice.
Interesting. Okay, so I'll back up a step to kind of show you all that.
It also looks like the address of where it removed is in that comment too. If you double click the address in there, it'll take you to it on the left.
Okay. So yeah, a couple things there. So up at the top here it said we have a warning that it's removing some unreachable block. So what you just mentioned here is we can double click on that address, and that brings you to the code block that's not being displayed there. What Bailey was also saying is we can have the decompiler still show us those even though that code block appears to be dead. And the way that we would make that show it is if you go into Edit, Tool Options. Underneath the decompiler, you have the analysis settings. And then if we uncheck the Eliminate Unreachable Code Block and hit Apply. Cool.
It's false.
The C code looks a little bit weird, but at least I guess we can see what was missing there. That's pretty cool. Okay, so we made our patch. We're pretty happy with how this code's going to function here. The graph view doesn't really show much different. We still see that if-else in there, but looking at our decompiler view and what we've seen so far, we can assume that this is always going to print out that we've got the correct product key. So the next thing we have to do is figure out how do we export this binary. I've had mixed results with Ghidra's built-in binary export function. It seems like if it detects that it was an ELF file or a Windows PE file, and you make some sort of patch to it and export it, that binary that comes out doesn't always work. Like it doesn't put the pieces back together correctly all the time. So there is a script that we can run, and I've put it in the GitHub, so we're gonna have to import a folder and run that script, and I've had just better results with it. So we'll go ahead and try that out here. So Ghidra has a pretty powerful scripting engine in it, and you can access it by hitting that green play button. And there's a whole bunch of pre-built scripts in there for you. And it's kind of a hodgepodge between Java and Python. And everything I think is kind of moving towards Python, but just Ghidra being built in Java, you're gonna see a lot of that stuff in there too. Does anyone program in Java? Okay. So, yeah, I don't know, at DSU we're always a C school, so we kind of have that inversion to Java. I don't know why, it's just how it is, but if you know Java, you're probably well set up for that. So what we're gonna do here is, if you kind of look at the left-hand side, you can see all sorts of different categories of what scripts are in there. So we need to import a new folder though that has the script we want. So up in the top right-hand corner, there's the Manage Script Directories button. It's kind of between that green refresh button and the red plus sign there. When you click on that, go ahead and hit the green plus button. That opens up your file browser. browse to wherever your GitHub directory is at, and then import that resources folder. So after you import it, you should be able to see that path at the bottom in green. This hasn't actually loaded the scripts from it yet, so what we need to do is click on that green refresh button, and it'll parse through all those directories and find what scripts exist and then automatically import anything that it finds that's new. So after it refreshes, on the left-hand side, go to the binary folder, and you should now see a binary export.javascript in there. And that's the one I like to use to write these patched binaries out. I've had good luck with it in Windows and Linux. 32, 64-bit binaries, it doesn't seem to matter, it works really nice. So to actually run it, we'll just double click on that script. It's going to open up a file browser and ask you where to save it. I'm going to throw this out to my desktop, and I'm going to call this hacks.out. And when you've got that done, you can go ahead and close the script manager and go back to your terminal here. So I'm still in my desktop folder. If we do an ls, we can see our new hacks.out file. Just because of the highlighting of those files, I know that this one's not executable because it doesn't have that teal green color on it. So we're going to make it executable with chmod plus x. Anyone remember what the execute permission is in decimal? Should just be 1, right? So we can change it that way, but the plus x is so much easier. So after you make it executable, go ahead and run it. Then whatever number you enter in here should get our full version of the product. And just to prove that wasn't a lucky guess, we can do it twice in a row. So it should be good.
Is this the typical way that people put out hacked versions of applications for sharing on Pirate Bay?
Yeah, I would say this is one of the strategies, right? If you don't know how they're generating the product key, and you can just bypass the check, it's a more straightforward way of it. We do have some CTF challenges where I actually have you figure out my algorithm for generating the user's PIN number. And so you actually have to do the math, and I'll give you an input and you tell me what the calculation would be. But most product key generation things aren't quite so trivial, so you'll see more stuff like this happening. So one thing I wanted to point out too, when we're patching code, we have to be careful with how big of a patch we're putting in here. So the instructions that we patched were on this compare line here. And you can see the bytecode on the left-hand side is a 39C0. So any change I make to that line of code has to be 2 bytes or less. What happens if I make too many bytes? Yeah, we start overriding other instructions and all of our pointer offsets are off, and that program's most likely just going to blow up. What could I do if I didn't have 2 bytes to patch? Like my patch was only going to be 1 byte, and I have 2 bytes worth of space there. Do what? Pad it with? Yeah, we could pad it with a nop. So if my patch was only going to change this 39 instruction here, and I didn't have anything to put in C0, I could put in that nop or that no operation, which is hex 90. And that's a valid assembly instruction. It just says do nothing, move on to the next step there.
Could you just do a jump to the bottom of the program and then add as many statements as you want, and then a jump to return? Like you could insert lots of data that way.
I'm not sure. So theoretically, your pointer offsets above that would be okay, but I don't think you can expand it. Andrew, do you have any?
So every change that you make in the size of the code, increasing or decreasing the number of bytes, is going to affect the offsets, the calculated offsets of everything after it. So while it is possible, the ease of doing that is going to diminish the more that you add. So I think theoretically for a small program, if you were adding or removing 1 byte, you could probably go through and fix all the offsets and make it work. But that's going to be really, really hard on a larger scale. Yeah, I think I would not recommend doing that value. That's going to be the more difficult.
But like, if you wanted to jump past like all of that code that is for that application into a new section of memory, could you do that?
Oh, certainly, yeah. I mean, you could just knock out the next 40 bytes or jump to the end of it. Yeah.
So we could change this instruction if we wanted to just jump to a different arbitrary location. So if we were to do the same type of patch, so if I right click it, go to patch instruction, and we change this jump not zero to a jump, and then just give it some arbitrary memory address. Like, let's say we wanted to go down to invalid key. Right, we could jump to this line here where it's 11,232. So our patch is going to be, oh, that is actually the line. I don't know, that's an invalid memory address, but.
Oh, there you go. Well, the fact that you're not using a block of code further down gives you space for you to repurpose those opcodes.
Ah, I see what you're saying. So, yeah, our program says welcome to full version. You're talking about this space here in that dead code.
So you'd have that many bytes to work with to modify to your desire.
Yeah, theoretically that should be fine as long as you're not making more space than what's allowed there.
So as Mike was talking about patching binaries there in different situations and use cases when this might be helpful, it brought to mind a story that I heard from, well, it's been a couple of years ago now, from 2017, about when Microsoft used this technique to patch a binary like in a defensive, good, security-minded way.
Did they lose the source code or something? Or?
Yeah, yes, quite literally. So in Microsoft Word, there is a little tool called the equation editor. And if you're going to be like writing out math equations in a Word document, you open up this separate tool and it does some kind of math ML, like you could draw up all of your math equations and it inserts it into the Word document. And it turns out that tool was written long, long ago, like in the early 90s, I think, by a third party. And a security researcher was interested in finding 0 days in Microsoft Word, and so they ordered all of the DLL files, the libraries, by age of compilation, found the oldest one, assuming that the oldest one will be the most vulnerable, the most problematic, and sure enough, they found some blatant buffer overflow vulnerability, like code execution, just easy, no memory protections or anything. They published this. But Microsoft did not have the source code to the equation editor to fix it because it was built by a third party in the 90s and the code was literally gone, couldn't find it. So what did they do? They used binary patching to like somehow fix the line where the buffer overflow occurred to solve the security issue, and they pushed out that new patched binary as an official Microsoft patch.
Of course they did, yeah.
Which, I mean, honestly, like, it sounds kind of silly and janky, but what else are you gonna do? Like, it's kind of a clever fix, right? It's kind of neat to see. So, yeah, funny example of when this can be used for good, not just to put things on the pirate bay. But that too, I suppose. So,